In this video I will talk about the buoyancy. We will see why it occurs, and also we will look at some of the applications. So let's talk about the applications first. I'm sure you must have wondered that why ships float, or like why blimps or air balloons float, or even why hot objects cool down. Okay, even though there is no external source which is supplying air, like I mean, even if there is no fan which is blowing air over a hot object, so why do they cool down? They do cool down due to the reason of buoyancy, and of course there is some radiation heat transfer which will also cool them down, but the buoyancy also plays a significant role there, and we will talk about these. These are some of the applications, but let's look at why actually the buoyancy occurs. So let's suppose if you have an object, and this is true for not only for submerged bodies in a fluid, but they are also, it's true for even the floating bodies. So let's just for now, let's just take an object which is actually is inside a fluid. So just some random volume I have, and what we do know, and if this is the fluid surface on the top, so fluid surface, and this is completely fluid, and so on. The pressure in a fluid goes down, pressure in the fluid increases as we go down in the fluid, and which is given by the relationship pressure is equals to gamma times the h. So as we go, this h keeps on increasing, the pressure will keep on increasing. So if I mention this height, which is somewhere over here, is h1, and then I have another height which is h2, which is up till the bottom of this object. So I can write this. Okay, so I have a pressure P2 acting upwards, and I have a pressure P1 acting downwards. Okay, so that is represented by this height h1, and that one is represented by height h2, and we can see that P2 is greater than P1. Okay, so P2 is greater than P1, so I can write this as P2 minus P1 is equals to gamma h2 minus h1, because you have the same gamma, so I'm going to take that common, and h2 minus h1. And I can also balance the forces, and I can assume that this area is the same, even though the equation will end up the same, but I'm just assuming that this area is same as whatever we have on top. So I can write this as F2 minus F1 is equals to gamma h2 minus h1 times the area, the surface area over which this pressure force is acting. And this difference of the forces, I can write this as F of B, which I'm calling as the buoyant force, gamma times h2 minus h1 times the area, or FB is equals to gamma times the volume. Okay, so this is the volume. So where gamma is the specific weight, and volume is the fluid being displaced, so this is the specific weight, and this is the volume displaced by the fluid. Okay, and this is some force which actually will be acting upwards, because you have a high pressure down below and you have a lower pressure on the top. So the net effect will be, there will be a net force acting upwards, and the location where that force will be acting is at the centroid of this geometry. So whatever that geometry is, it will be acting at the centroid, unless your gamma keeps on. So this is true when your gamma is constant for the fluid, but if the gamma keeps on changing as you go down in the fluid, then this force will act at the center of gravity. Okay, so if gamma changes, then the buoyant force, which actually acts upwards, will act at center of gravity. Alright, so it will X center of gravity, and as you can see, due to the pressure differences, there will be a net force upwards. Alright, so, and not only, I mean, this is not only true for if you are in liquid, but this is also true when you are in an air or in some sort of gas. Alright, so anything else I want to say about this? So that's pretty much what I wanted to say about the buoyant force, which actually will be acting upwards. And if you notice, as I mentioned this, so it will be gamma times the volume that will be displaced by the fluid. So if you have an object, and this is some volume, like it can be anything that you drop in a fluid. Okay, so now you have a higher pressure P2, you have a lower pressure P1. So if the object is actually, I mean, the way it happens is if there is no object and this is just fluid, as you go down in the fluid, and if I take this as a fluid element, so this is fluid, you still have the higher pressure on the top, you still have a you still have a lower pressure on the top and you have a higher pressure at the bottom, but this fluid does not move up and down even though if it's the same fluid. The idea is the forces are balanced by the weight of this object. Okay, so if this is the same fluid, and I can write this as F2 minus F1, again you will have to also balance the weight, so the weight is also acting downward, so this is A and then is equals to 0, so there is no fluid movement. But now if you replace this fluid with something which is heavier, okay, so the fluid that will be displaced, as you can see over here, if that object is heavier it will sink. If that object is lighter, in case of a balloon which actually is filled with air, so air is much lighter compared to if you displace the volume of water, so the air, so the balloon will be pushed upwards. But if you're talking about an iron, and compared to the volume it will displace, so the iron will actually be heavier, so that's why it will sink. So that's what this relationship tells us, that if you so that will be the net force upward based on the amount of the fluid that's being displaced. So this is the gamma of the liquid and this is the volume. You can think about it of the fluid volume that's displaced or the volume of the object that you're inserting inside the fluid. Okay, so the next thing is again, we also, like as regular human beings, so let's suppose if our weight is, or our mass is, for an average human being, so mass of an average person is somewhere around 72 kg. Okay, so the weight then becomes 72 times 9.81, so weight is m times g, so 72 kg plus meters per second squared, so this gives you 705.6 Newton force. So a person, I'm representing that person with the cylinder because it's just much easier to do the calculations for the buoyancy. So the weight of that person is 705.6 newtons. But I can also assume that if that person has a so I can take the diameter, like that person, head and everything, shoulders and everything, so I can assume that that person has a diameter of 0.25 meters. Okay, so that's diameter. The height of that person, I can take that to be 1.75 meters. So this gives me a volume, so I can compute the volume, which simply is pi r square L, which is pi r square times the length will give me the volume, and if I do the math and everything, it gives me approximately equals to 0.085 cubic meter. So that will be the volume of that person. And if you're talking about in air, so I can take the gamma of the air at 20 degrees equals to 11.81 Newton per meter cube. So if I look at the buoyant force that are acting, so again, if the person is standing in the air, even though the weight is pushing him down, but at the same time there will be some buoyant force which is pushing him up, because the buoyant force is basically that pushes that person up. So that buoyant force will be equals to gamma of the air times the volume that will be displaced by the fluid or from that object. So I can write this as 11.81 Newton cubic meter times 0.085 cubic meter, and all of this put together, it gives me approximately equals to 1 Newton. So that is the reason. So you have a 1 Newton buoyant force compared to 705.6 newtons of the force that's this person is exerting on the earth. So that's why we neglect this buoyant force, and we just take that to be so we don't include that. But if you are talking about in terms of water, so if the same person actually goes inside the water, so the gamma of the water actually is, so gamma of water is actually I think it's so almost like 1000 times of gamma of the air. So now the buoyant force actually is much larger. So the buoyant force approximately equals to be maybe like, yeah, I mean for that person, if you just multiply that with 1000, so I mean it's a much significant force. So that's why people tend to float, because they have so the natural inclination is that you will more likely to float. So yeah, I mean, yeah, I have to look at this number, but somewhere around this, that's the number we have for the water. So the buoyant force when you're in water is much more than when you're in air. All right, so let's actually, okay, so a couple of things. So let's look at 3 possibilities. Okay, so the first possibility is, so let's suppose this is a liquid layer. So this is where you have the liquid. So the first one is, so this thing is actually floating. So that happens when F of B is much greater than the weight of the object. Okay, and then you have F of B is equals to the F of B is greater than the weight of the object, and then you have F of B is equals to the weight of the object, and that is the case when this object actually is suspended in the liquid. So in the first case, the density of the object is less than the density of fluid. In the next case, the density of the object is same as the density of the fluid, and in the third case, when this thing actually will sink to the bottom, we have F of B is less than weight of the object. So that is the case when the density of the object is actually greater than the density of the fluid, and so this will actually have a much higher weight, so that's why it will sink to the bottom, and the others will actually either they will be suspended in the fluid, or in this case they actually will float. And this is the reason that actually the ships and all that, they do float, even though they have a much like, because you're using iron and so on, so they are much higher. I mean, they have their density is much higher, but the amount of the fluid that they have to displace, so if I'm looking at the ship from this side, so the ship actually goes something like this. So now the idea is, as the ship goes down further, so it's not that the fluid is actually going from the top, otherwise the ship will sink if it's completely submerged. So there's a lot of air, and also there's of course there's iron, but there's a lot of air, and the net effect is the amount of the fluid that it will displace. The buoyant force is much higher than the weight of the ship itself, if it's with the air and all that. So that's the reason it will float. For small objects, the surface tension will let them float, but for big objects, it's only the buoyant force which will let these objects actually float. Alright, so let's actually take a look at an example. Okay, so the example says as follows: determine the volume and density of an irregular object based on the following set of data. So in this example, we are trying to find the volume and the density of this irregular shape, and we have this scale, and based on, depending on how we take the measurements, so mass in the air. So for this irregular volume, the mass in the air came out to be 27.2 kg. And if I fill this bucket with water, because now you have water which actually has much higher which has a much higher buoyancy force, so the mass in the water of this object will be smaller. As you can see, it is 21.09, and what we want to find is the volume and the density of this object. So and also we can actually do this experiment not only in air. You can take this as oil, you can also take this some other oil, and then you can do the comparison. So basically we are trying to do the comparison study. So let's actually take a look at how we will solve this problem. So alright, so we have mass in air equals to 27.2 kg, and then the mass in water is 21.09 kg, and I can write this as so for air, let's look at the apparent weight. Okay, so apparent weight is W apparent weight in air is equals to the actual weight, and I'm representing this actual weight when you don't have any buoyancy. So basically if you measure this in vacuum, you don't have any fluid, so there is no net force pushing it upwards, so that is I'm representing with W, and the apparent weight is what you will get from that scale when it's suspended in air or in water. So the apparent weight in air is equals to W minus the buoyancy force due to air. Okay, and in a similar way I have for the water. So for the water we have an apparent weight of in water is equals to weight minus the buoyancy force in water, and I can write this as the weight is equals to the apparent weight in air plus F of B, or the buoyancy force in air. And I can also write this as W is equals to the apparent weight in water plus the apparent weight in water. The apparent weight in water plus the buoyancy force in water. And now I can substitute these weights equal, and I can write this as apparent weight in air plus the buoyancy force in air is equals to the apparent weight in water plus the buoyancy force in water. And then I can also I can move those on one side. I can take this as the buoyancy force in water plus the buoyancy force in air is equals to apparent weight in air minus the apparent weight in water. Okay, so once we have this, I can write this I have the gamma of water times the volume that it will displace plus the gamma of air times the volume it will displace, and then I have this weight of this object which actually comes out to be so 27.2 kg times 9.81 kg meter per second square. Actually this is just meter per second square minus 21.09 kg times 9.81 meters per second square. And if you'll notice, I can take this V out in this equation, so it's just V times gamma of water plus gamma of air is equals to 27.2 minus 21.09 into 9.81 meters per second square. But now I can realize one thing, that the gamma of water is much greater than the gamma of air, and we do know this, that the gamma of water is, I think, is 1000, and the gamma of air is maybe 5 or 10. So we can basically neglect this, so this approximately goes equals to 0. Okay, so something we can as an engineering students or as an engineers, we can make this assumption, because it really does not change the solution that much. So I can write this as gamma of water times the volume is equals to 6.11 kg times 9.81 meters per second square. And then I have this volume, which is equals to 6.11 kg 9.81 meters per second square, divided by gamma, which we do know that the gamma is equals to rho times g. Okay, so rho times g. So I have this thing as rho of water times 9.81 meters per second square. So these cancel out, and we are left with 6.11 kg divided by 1000 kg per meter cube. So I can take this density of water to be around 1000 kg per meter cube. So this gives me a volume of 0.0611 cubic meter. So that is the volume of this irregular shape. And in a similar way, I can find the density of this object. So density of this object is equals to mass over volume. So I can take this mass inside the mass in water, and then I have this before I do this, I want to show something. So we will be using this relationship, but I will now be using the mass in the air. Okay, so mass in air divided by the volume, and let me show you why we are actually using the mass of the air and not the mass of the water. Okay, so we have the volume now, and I will also use this relationship to find the density of the water. Okay, so as you recall, we have this relationship where we have the mass of the apparent weight in air is equals to the buoyancy force in the air, and that was equals to W is equals to W apparent plus the air. Okay, so I can neglect this, the buoyancy force, to basically get out the actual W. Alright, so either I can neglect this, which is a very small quantity, or I have to either use this relationship in water is equals to W minus FB in water, and it will be the actual W that I'm looking for, because that will give me the mass, the actual mass that I want to find the density through, and not what we are actually getting from the scale, because that also includes the buoyancy force. So the apparent weight in water plus FB of water. Okay, so either I use this relationship to find W, or I can use this relationship to find W. So both of them will give me the same W, because we have the buoyancy force, we have the volume and everything. But this is much simpler, because again, we can find this quantity also, but if I just neglect this, as if this approximately goes to 0, so W is the same in the air as the apparent weight in air. So this tells me that the mass is basically the mass in air. Otherwise, I will have to look at this W to find the density, so it will be the mass in the air. So now the density is mass in air divided by the volume, and we have this as 27.2 kg divided by 0.00611 cubic meter, and the density comes out to be 4 451.72 kg per meter cube. So it is the mass of the actual object, and in this case I'm just saying that because the air does not really affect the apparent weight that much, so I'm just making those equal. But if you're taking the mass in the water, then you have to include that buoyancy force. Alright, so here is the first example that I just did for the buoyancy, and let's actually take another example and try to see how this problem can be solved using buoyancy principles. Alright, so this example I took it from the Fundamentals of Fluid Mechanics by Munson, and what it says is a spherical buoy has a diameter of 1.5 meter and weighs 8.5 kilonewton and is anchored to the sea floor with a cable. If the buoy is completely submerged, find the tension in cable when the specific gravity of salt water is 1.03, and I can take the density of water to be 1000 kg per meter cube. Alright, so we have this buoy that we want to find out what the what the tension in the cable is. So tension in this cable. So to solve this problem, I actually have to draw a free body diagram. So I'm going to look at this buoy here. Okay, so which is completely inside the fluid, and that's why there is a buoyancy force acting in this direction, which should be at the centroid of this geometry. So that's where our buoyancy force is acting. The weight is also acting at the same point. So if I'm thinking about it, so the weight also I really can't say where the weight is acting, but because it should be acting at the center of gravity. So we don't know if it's hollow or something, but the weight is acting in this direction, and then the tension in the cable it's in this direction. So this is tension in the cable, so I can make them equal. So I can take going up is positive, so I can make this as so summation of forces in the y direction is equals to 0. So I can make this as my y-axis, this as my x-axis. So anything that goes up is positive. So T plus FB minus W is equals to 0. Okay, so if I have this, then I can write it as T is equals to W minus F of B. So to get the tension in the cable, I need to know the weight and then the buoyant force. So to get the buoyant force, which actually is equals to gamma times the volume that it's going to displace. So this is a spherical, so I do know what's the volume of sphere. In this case is 4 by 3 pi r cube, and we are given the diameter, so I can convert this into radius and everything, and it gives me 1.76 cubic meter. So that's the volume, and we also have the density of water. So this gives so the specific gravity, so we can find the specific weight based on that. So the specific weight is simply density times g. Alright, so once we have the density of that object, so in terms of specific gravity, so I will multiply that with the specific gravity times the density of water times the acceleration due to gravity, and when I put these together, so basically this is 1.03 times the density of water 1000 kg per meter cube times 9.81 meters per second square. So all of this put together, it gives me 10.1 into 10 raised to power 3 kilonewton per meter cube. So we also have the specific weight, so we have the volume and specific weight, so this gives us the buoyant force of 1.785 into 10 raised to power 4 Newton. So we have the buoyant force. The weight of this thing was given to us in the problem statement, which was actually 8.5 kilonewton. So the weight of this object was 8.5 kilonewtons. So when I solve these things together, it gives me a tension of 8.5 kilonewton minus 1.785 into 10 raised to power 4 Newton. So it gives me a force of alright, so this is 10 raised to power 317, so it gives me a tension of minus 9.35 kilonewton. So what that tells me is that the assumed direction of this tension is not correct, so I have to actually choose it in the other direction. So it should be in the other side, so tension will be this way. So this negative sign represents that I did not choose the correct direction for the tension, but the magnitude is is 9.35 kilonewtons. Alright, so in the next video I will talk about the stability of the floating objects. So we found out what the force is acting on these object, and in the next video I will talk about the stability. But let me just go back to one last time to the applications. So why hot objects cool down and or like the ship's float and everything. So I did talk about the ship, but what happens in a hot object, so let's just suppose that this is a hot object somewhere sitting over here. So anything, of course there will be a radiation electromagnetic waves that are leaving and is cooling this object down. So this is a hot object, but at the same time, as soon as the air gets in touch with this hot object, so as the air heats up, the density of the air actually changes. So its density is lowered, and what happens is as the density is lowered compared to the surrounding, it feels a net push upwards, and then the cool air, which has a higher density, comes and tries to fill this gap in, and then when it gets in contact with this hot object, its density also reduces, and as the density reduces, it will feel a net effect upwards, and that's why the air current will start flowing this way. And in fact, our weather patterns also change because of this. Anytime you have a hot surface, the density of the air will change, and it will create a low pressure region, and then you have higher the air will try to come in and fill that low pressure region. So there are a lot of applications of buoyancy, and so I just discussed few. Alright, so I will see you in the next video on the stability.